Hi, welcome to this webinar. I am Gabriel, the sales engineer here at EnGenius, and we're actually going to talk about TDMA or EnGenius TDMA. You'll see later on what I mean by that. And it's ours is called EnJet. So the title of this is Time to Jet Through Outdoor Limitations, and I couldn't add it because it was too long with EnJet. So without further ado, let's get started. Okay, so we're going to go down some quick terminology first. It's important that we have at least a baseline of what we're talking about. We could build upon that. And then we have CSMA and CA overview. And some people may be wondering what that is. That's basically the standard Wi-Fi way of communicating. Stands for Carrier Sense Multiple Access with Collision Avoidance. And then we're going to go through TDMA overview. So we're going to see the standard way of doing it. And then we're going to see what TDMA brings to the table. That's different than the standard way of doing it. And then we have our EnJet design and setup best practices. And just because we have TDMA, we still have to follow certain rules. And then we're going to follow up with questions and answers. Okay, so this webinar is actually provided for the partners. If you're not a partner, we would highly suggest that you become a partner. You have access to things like free network design tools, access to sales and marketing tools, channel advantages, a dedicated support team, trainings and certifications such as this webinar right now, and access to discounts from certain distributors, access to certain products before we fully release them. Events, we just recently did an event with a cloud launch for partners. They were the first ones to be invited. They got first dibs on that. So we highly suggest that you go become a partner, elite partner, and to gain all the benefits and further benefits in the future. And if you want to know more about it, just go to www.engeniustech.com/partner-program or email partners@engeniustech.com, and we'll get right on it to helping you out to become an EnGenius partner. Thank you for that. Okay, now let's get started with these quick terminology. Okay, so when you're starting off in networking, they'll teach you things about network topologies, and basically there's two major types of topologies. There's a physical and a logical, but there's also, when we're starting to talk about changing the signaling methods, there's also a signaling type of topology. And so we're going to add that here as a third type. So the physical one is, I think most people are familiar with it. It's the switches, the cable connecting to the switches, the routers, things of that nature. Then you have the logical topology, which is like the high-level overview. An example would be if I was drawing two routers connecting over the internet, I'll just draw two routers and then a line through it through a cloud. Well, the physical one looks different. I'm going through different switches, different routers over the internet, but I'm not going to draw all that because it's just going to take up too much space. So the logical one is a high-level overview. The physical is the actual physical one I'm touching. There's also something called signaling. So the signaling topology basically is how is the network going to flow through the, how is the network traffic type going to flow through the network? For example, if I was using a circuit-based one, I could know what the actual circuit is. But if I'm using a frame relay or something with a virtual circuit, I cannot determine how it's going to go through the entire network the entire time, but I know what it's going to go through in a small scale, and that I could draw out. And then as it goes further on, it's going to look less predictable. So this is important because we're talking about TDMA over standard Wi-Fi chipsets. The physical topology is going to look one way. The logical topology may not match the physical topology, and the signaling topology may be something different too, and may not match either the physical or the logical. An example of this is the one where you see the four computers and the device in the center hooking up to the printer. So in the device that it's highlighted in the red box, if that was a hub, I would have this actually in a physical star topology. The logical topology would be more like a bus. And the actual signaling would be like a line or a bus. So in that case, you would see that the logical topology does not meet the physical topology. Now, if I actually change this to a switch, the logical topology will be a star. The physical topology will be a star, but the signaling technology will be a point-to-point. Because in a switch network, it's called a microsegment. Every single segment is segmented off and considered its own segment if it's non-shared. So that's one example of how a signaling topology, a physical topology, and a logical topology don't necessarily have to match. But it's important to understand so you could see how the traffic is going to flow down the network or predict how it's going to flow. Okay, now we have the duplex communication types. We have simplex, half duplex, and full duplex. So simplex is something that we readily understand. The example shown here, the TV station transmitter, and then we have an antenna that's dedicated as a receiver. So one device is dedicated transmitter, the other device is dedicated as a receiver. So one will not do the other, like it is for the other duplexes. So in this way, it's only one direction type of traffic. It does really good with that. But if you need bidirectional traffic, you have to go to either half or full duplex. In half duplex, you have two-way communication, but only one vector at a time, only one direction at a time. So a device can only talk or listen. It can't do both. And Wi-Fi is a half duplex communication method. So you would see, as we go further on, when TDMA is deployed on Wi-Fi chipsets, you still have to be constrained by the actual chipset limitations itself. And that's one of the limitations. And full duplex means that we have communication in both ways at the same time. So we, just like Ethernet, or you have two separate radios, different frequencies with a multiplexer chip to give you the illusion of a full duplex. Okay, so now let's talk about standard carrier sense multiple access with collision avoidance overview. This is the way standard Wi-Fi operates. So how it would normally go is that the RF radio has a front loader onto it. It's not a physical front, it's a physical one, but it's software controlled. So they're going to software offload the front loader so it can have exposure to raw RF energy that is not it's not been manipulated by the front loader. So in this case, it's going to offload the front loader. It's going to check a particular frequency spectrum or the entire spectrum. It really depends upon the vendor. And what it's going to do is going to check to see if it detects any raw RF energy that hits a certain threshold. If it hits a certain threshold, it's going to turn on a random backoff timer. And when the backoff timer expires, it will run the same check again. And this time it's deferring transmission. This is what we normally would refer to as interference because it's raw RF energy, as opposed to the next step, which is contention, which we'll talk about in the next step. So in the next step, we're going to load the 802.11 software front loader back on. And now what's going to happen is as the RF signals go through the front loader, it's going to filter out anything that's non-Wi-Fi 802.11, only let me see the things that are filtered 802.11. In this case, I'm looking for a particular type of timing in this case. I'm looking for something that we call a nav ID, and this is what we call virtual carrier sense. So in this way, what happens is that when the Wi-Fi wants to communicate, basically it gives an estimated time on how much it's going to communicate, how long it's going to communicate for. So if I'm joining in on an access point, it's currently communicating to someone else, I set my timer to whatever the timer is for that person said they're going to take. Once that timer expires, then I could contend for the medium. If I win access, then I win my transmit opportunity, then I could transmit as well. And I could do the same. I could set my duration of conversation and people could adhere to that. That's called a nav ID, called network allocation vector. And this is what we normally call contention. So as you can see, those are two separate things. The interference is raw RF energy. Contention is only for 802.11 type of energy. And basically, if the funny thing is in Wi-Fi that if the timer is 0, that means to actually take an action. So in this case, if I was to, let's say the scenario, I was already participating in the cell and someone communicated and I lost my transmit opportunity, I still have my timer going. And when that timer expires, I am able to communicate again when the other person stops talking. So I add that person's time to my time. Once the total timers expire, then I check for a DIF S frame time slot, and then I am able to contend for the medium. If I win, I could transmit. I know it seems like a really, really long, complex one. It's really oversimplified actually. And the reason why we're talking about this is because we're going to show you what TDMA communication looks like after we explain what it is. So in this case, the nav ID is 0, it wins transmit opportunity, and it transmits the frame. In the TDMA overview, basically, TDMA stands for Time Division Multiple Access. TDMA is the channel access method for a shared medium networks. So TDMA was first used on wired networks, ThinNet actually, coax back in the day. And it worked well for those type of networks. It was a ring type of logical topology, and the signaling topology follows exactly, TDMA follows exactly that perfectly, perfect. But as time progressed, they were able to put TDMA on other type of communication mediums that were multiple access. For example, TDMA was around the cellular networks around the 2G timeframe to be more efficient with their medium. This was before OFDMA became available for them. And now, you know, with OFDMA, TDMA goes in conjunction with it, but it's really less of a player now with that. It's what we call a deterministic type of communication protocol, which means a device determines the time slot. So it's not non-deterministic as CSMA CA is. That basically is a distributed type of communication protocol in which the method for communication is distributed amongst all the clients. In this case, it is centralized. So the centralized, point source coordinator function actually determines who could talk, who cannot talk based upon the time slots. And it comes in two different flavors, actually. It comes in a symmetric and asymmetric. So in a symmetric TDMA, basically there's fixed time slots. So everyone gets the exact same time, whether they need that time slot or not, whether they're going to communicate or not. So as you can see, if, let's say, for example, client B has nothing to communicate, well, it's still given a time slot. So that's kind of wasting my airtime. And when that's the case, I'm actually able to push less throughput through. But let's say B needs to communicate a bigger time slot than it currently has. It has to fragment it. If it fragments it, it has to wait for the entire carousel to go around before it communicates again. So as you can see with TDMA, as you start getting more participants join in the TDMA domain, the time slots, if it's fixed, start to become less and less. You get statistical access to it, and then that means that basically if you have things that need it, you're going to miss out on your opportunity to communicate. So asymmetric TDMA was developed, or dynamic, whatever you want to call it. Basically, this one actually adjusts the time slots. So to adjust the time slots, basically, if you want to communicate more or less, if someone is not going to communicate, their time slot gets less. They still get a time slot, it's just less. In this case, there needs to be a feedback mechanism. So what happens is as the timing goes around the carousel, if I need more, I'm going to throw a flag. That flag comes back. And when that flag comes back, the point source will, if there's enough resources, will allocate other resources for other people that do not need it to take up their time slots. And now I'm able to use that time slot during my carousel time. So this is very good for actually having people on the same frequency use that frequency better. And so this is the reason why TDMA is much more efficient than other types of communication that we have, such as CDMA coding or a FDD, frequency division as well. So one thing to note about TDMA is that it's on a standard Wi-Fi chipset, and those Wi-Fi chipsets are normally not highly calibrated or a higher price. Such as when I'm doing TDMA in cellular, those radios are higher price, more precision calibration, more tolerances built within them. In Wi-Fi, if you're putting TDMA on there, you have to be able to adjust for that particular chipset. That's not really, as I would say, price point as much as the higher ones. In this case, we show an example here of a vendor. As you can see, it looks like garbage in the beginning. So it looks like in the beginning, it's not using TDMA. And then towards the end, it looks like it actually is. So you can see some type of frame structure. So when you see a frame structure like the one on the right-hand side of our oscilloscope here, you could say, okay, it looks like it's actually using a TDMA because the time slots are actually fixed. This one has a 20 megahertz channel size, about 40 CPEs. This is DUT stands for device under testing. So this is vendor A, this is vendor B, and as you can see, vendor B is much cleaner. It's actually using TDMA more often in its communications. And this is a 20 megahertz wide channel size with about 30 CPE. So CPE stands for consumer premise equipment. Basically, it is, they call it subscriber radios. They are the ones that are being tied to the main access point. So you call them like client bridges. And they actually have their time slot to communicate as well. And as you could see up in the example, in the blue arrows, the lower one is the client's time slot to communicate, and the upper one is the access point's time slot to communicate. So you would view the lower one as upstream traffic and the top one as the downstream traffic from the perspective of the main point source, the access point. And the red arrows show there's a variation of the times. And so we could determine that this is actually using asymmetrical TDMA because of the time slots vary. Another example too, in this case, the variation is slighter. So it's there's not really that much variation between the traffic or the clients on here. So it's looking more like symmetric TDMA, but due to the time slots being different, it's really not, but it's close. And then we also have the clients communicating back in the front end, and the back end would be the access point communicating to the next time slot. And this is a 10 megahertz wide channel size, about 40 CPEs in this particular one. The reason why we brought this up is because TDMA is not standardized in the protocol 802.11, so the vendors get to deploy TDMA in their vendor proprietary type of way. So not all TDMA is built the same. So if I have TDMA from one vendor, it may work better for a particular traffic type or a RF environmental situation than another vendor with a TDMA. So one thing that people run into sometimes if they just equipment swap is, you know, sometimes if they equipment swap and it resolves a problem, it could be that that TDMA that the vendor has was not an appropriate fit for that particular type of scenario, wasn't qualified appropriately for it. Okay, so now we're going to go over our EnJet overview for the EnGenius lineup. So there's certain models of EnGenius that do support TDMA right now. Not all of them do, but in the future they will. Some of those models are the EnStation AC version 2, the EnStation 5 AC version 2, the ENS 500 AC version 2, the ENS 500 EXT AC version 2. That rolls off your tongue quite nicely there. And there's the ENH 500 version 3. See, you're paying attention. There's a version 3 there. So this is what those devices look like. The EnStation AC and EnStation 5 AC would be in the lower left-hand corner. The ENS 500 would be in the lower right-hand corner. And then the ENS 500 EXT AC would be in the one in the middle. And then the ENH 500 would be the top or right-hand corner. That's the one you would see there. And you could see that we actually have screenshots of one. So you can see if you're on the live feed, you can see that. Okay, one of the questions we do get a lot is how do I tell if it is hardware version 1 or hardware version 2, whether it supports TDMA or not, or whether it has it in there? Well, one way to do it is checking the stickers on the back. So here's an example of the stickers we have for a version 1 and version 2. Version 1 is on the left-hand side and version 2 is on the right-hand side. As you can see, version 1 does not denote anything about a hardware version or a different model version. Hardware version 2 actually denotes that there's actually a change with the version number, with the version 2, which is highlighted in the particular slides. Another way to determine it is if I log into the user interface. Let's say I don't have access to the device, to the box, to the sticker. How do I determine at this point? Well, if you log into the device, if you go under Overview Device Status, you would see on the left-hand side that's a hardware version 1. It does not state anything about device version. In the right-hand side, you could see device version. It is actually denoting a 2. So I could tell that this is a hardware version 2 of that model. Another way is the firmware upload section. If I go to System Manager and Firmware, in the version 1, it will not denote anything about it having a different version of firmware to check. For hardware version 2, it'll denote the version is 2, and then I'll have a note of a kindly reminder. It states kindly verify the device version when upgrading firmware to a new one. If you do not, the corresponding version of the firmware upgrade process will fail. So yes, it's not advisable to put hardware version 2 firmware on hardware version 1 and vice versa. Another way to determine it is if you actually go to the network in the wireless section, you would see whether or not EnJet is actually there to enable or disable. On the left-hand side, you would see there's hardware version 1. That is basically denoting nothing about EnJet. In hardware version 2, there is an EnJet one to turn it on or turn it off. And that's how you could determine whether you have hardware version 1 or hardware version 2, or a combination of all of these. So why is TDMA or EnJet important? Well, it's important because this is what it changes in the process of the communication on the wireless chipset. You could see there's really nothing new here. Basically, it does the same check as it does for the ED check and 802.11 chipsets for CSMACA. It is offloading the front loader, it is checking the raw RF energy, and it's determining whether or not it is going to hit a certain threshold for deferred transmission. If it hits a certain threshold, it's going to set the random backup timer. If it doesn't, it moves on to the next step. The next step is bang. I just transmit the frame. So long as I'm participating in there and my time slot is around the time in which I'm supposed to be doing this, then I transmit the frame. So there's, as you can see, we remove a lot of the other checks that we have, the virtual carrier sense, and now we just have the physical carrier sense. So as you can see, TDMA would be very good or very deployed in well areas such as high contention areas. That's the reason why I like to save is high contention. You probably might be looking at TDMA as one of the tools in your toolbox to get proper wireless communication as opposed to standard Wi-Fi. So now you have EnJet design and best practices set up. So if you have these technologies such as with TDMA, or I've even heard it with mesh, it does not change the physical properties of the underlying radio underneath or the physics. For example, if I have TDMA, it doesn't mean that I could deploy it with a cell phone tower next to me that is interfering. That's not going to help with that. Or if I have mesh, I can't automatically put mesh on a device and it'll now magically go through more walls. That's just not how it works. So one thing you should be asking is TDMA a good fit for this deployment? It's great that we have this tool, but it's not necessarily needed for every single deployment. Where it fits best is if you have fixed wireless, no roaming clients, because if the clients move around, it changes the timing. If the timing changes, it's got to be changed across the entire domain, and that requires more subframes to be with the timing and a better processor to be coordinating that. So fixed wireless is best for TDMA. It's a steady, non-bursty traffic. So if I have traffic that's predictable, and in such as, let's say I have camera traffic, and that camera traffic I'm using ABV. I'm using nothing that's going to change my bit rate. Well, if it's a steady bit rate, then I know what the time slots it needs or how much data it needs. I can adjust those fixed time slots to be appropriate for that. Heavy traffic in one vector. So if I'm pushing traffic in one direction, for example, I'll use the camera traffic again. If I'm pushing a lot of upload traffic, then it'll be best for me to use TDMA because that's in one vector. So I don't need the ability for it to change direction, on the fly to be able to handle different traffic types. I'm sending just one traffic type down there in one direction. And high 802.11 contention areas. So as we stated before, condominiums, apartment complexes, things of that nature would be an area which I would deploy TDMA because if you've done a site survey in a condominium complex lately, you'll see that they are going into even DFS channels. So 5 gigahertz is starting to look as bad as 2.4 in some areas. Where it's not a good fit is a non-fixed wireless. So if you have roaming clients, it's probably not the best fit for TDMA to be using, but TDMA for Wi-Fi chipsets in this case. Variable bursty traffic. Let's say I have camera traffic plus web traffic plus some streaming traffic going down there. That's really not ideal for TDMA because these traffic types have different metrics. And because of the timing carousel, there's going to be an inherent underlying delay that's going to be on the network. So the standing latency would be higher on a TDMA network than a non-TDMA network. But the benefit I get of that is that I'm actually able to have more consistent, predictable, reliable traffic prediction as opposed to one that doesn't have TDMA. Heavy traffic load in both directions, up and down. As we stated before, when you have different traffic types, you have to change the timing on the carousels. That needs to change on the access point side as well as the client bridge side. And that it does require at least 1 to 2 carousel rotations for that to be inputted and to be adjusted. So that takes time. It's equivalent to like a turbo lag, in which when I apply the accelerator, I don't immediately get a boost. It takes time for it to dump it down so it spins up the fan and then applies the necessary pressure. So the same thing for concept for TDMA. It's not immediate. There's kind of a delay to get the benefit of it. High RF interference areas. So as we stated before, TDMA is great for contention, but because it still rides on a Wi-Fi chipset, it still has to check it for the physical carrier sense. So if you have a high RF interfering environment, it's going to impact it. So things such as cell phone towers that are close, that are leaky, maybe bad ballasts. I'm trying to think what else I've seen around here for 5 gigahertz have been causing problems. Let's say you deploy it next to a neon sign and that's leaking out a lot of RF all over the place, wideband interferer, that's going to cause problems. So things of that nature, obviously you want to be able to start switching to a different frequency to try to get away from that interference source. Another thing what we talked about earlier, which we want to go further in depth into, is called TDMA domains. So what even we have this problem with standard CSMA CA, and it's kind of more prevalent in that one. TDMA is kind of going to mask it and do a band-aid, but there's a point at which you could only cover it up so much before the problem starts to reveal itself. This is not a good way to deploy Wi-Fi either in standard CSMA CA or in TDMA. You have multiple clients that are only a certain feet from you, like XX feet, and then you have certain clients that are certain miles away from you. The distance between these And the timing distance is too great for TDMA to actually give you any benefits to this. And same thing with standard CSMA, CA. So because they're too far away with standard CSMA, you're going to have situations which the far client's not going to hear the near clients, and near client's not going to hear the far clients, and you have a higher cyclical chance of having collision. In TDMA, because it's deterministic, what's going to happen is the clients that are closer are going to actually have access to the time slots sooner than the ones further away. So that means that the ones that are further away are going to actually be not performing as well as the ones that are closer. So what you want to do is because most Wi-Fi TDMA is asymmetrical and not symmetrical. So in this case, what's going to happen is that the closer clients are going to have better access to the carousel time slots, and they're actually going to be able to win that time slot more often and be able to actually start taking the resources that the far end clients may need. So one way to fix that, and one way we always recommend, is to break up the domains. So as you can see, TDMA domain 1 is for the ones that are closer, and TDMA 2 is ones that are further. So then you don't have to really worry about closer clients winning the time slot or taking up a time slot sooner. Then they're all similar RSSI distance away, similar MCS rates. So the timing should be not that much of a delta between them. So the TDMA will shine better in that particular type of deployment. And we've seen this too with other vendors in which they have dual radio deployments, in which they have a radio servicing closer clients with a wider beamwidth, and then a secondary radio with a narrower beamwidth serving clients that are further away. And they're two separate contention domains, and they do a timing between the radios to try to coordinate the transmission and the receive so they don't step on each other because they're pretty close together physically. With that being said, there's certain options you could set in ours. And so we're going to go over them and what we recommend for you to deploy in. For the AP, there's something called the AP time slot. So this is going to be the one that's going to be controlling the time carousel. We recommend auto for majority of network traffic because a lot of people like to mix their network traffic. It's not one particular type of network traffic that we've seen. So they set it to so if you set it to a fixed time slot, what's going to happen is you're going to have the fixed TDMA, and the numbers of 2, 3, 4, 5, 6, 7 denote the frame size that are going for it. So the smaller the frame size, the quicker I can respond to people requesting, the less throughput they're available. So if they need small amounts of traffic and they're very latency sensitive and it's only one particular traffic type, I'll choose a smaller time slot, such as for VoIP. But if they're using large amounts of traffic and it's still set, you already know it's still set, so it's not like someone needs to win over the other, such as maybe for video traffic streaming going through in one direction, then maybe I'll pick a larger time slot. So I would have a little bit of wasted airtime space, but at least they'll give it a fair enough slot in which they could dump all their data into that particular slot on the carousel to go through. So one thing to note, that if you're setting the AP time slot, then you should not set the station priority. So the station priority should be set if it's auto. The station priority is going to be default high, but you can also set it. Now, if the other one's set for auto, then the station is now determining the time slot as opposed to the primary point coordination source. So this is great for dynamic TDMA. We recommend setting this to whatever you want. High, it comes default as high, so if they're all participating in the same domain, we recommend they all be of the same level. It is possible to do a mix and match, so some are low that are close to medium, that's in the middle, and high that's not too far away. We don't really recommend that because as you start getting more and more participants, then what happens is then the time slot you may want a time slot, may not get it. So it's recommended if you're doing the station priority that you set all the stations for the same priority so they all are have equal access to the time slots. So in this case, if you're setting the station priority, do not set the AP time slots as in the slide over here because they'll have a mismatch and you're going to have a suboptimal network to the point where it could actually even prevent the timing sequence going on between the radios. So not really, if you ever deploy TDMA, you'll know that there is actually a delay because the client has to have the timing of the primary source, or it can't put its stuff on the carousel. So that takes some time. sometimes it could take up to 5 minutes to 10 minutes. So when you first set up our devices in a wireless bridge and using TDMA, if you don't see it associated in the first 3 or 4 minutes, don't really be alarmed. Just give it a little bit more time in order for the time sequence to be distributed across the domain in order for them to be participating. Because as you add a new device into the network, let's say I have a point-to-point and I wanted to make a point-to-multipoint and add another one, well, then that one has to change the time slot for everyone because it's introducing a new time slot, and that'll be another slight delay of that. The delay is slower, about 1 to 2 minutes, but the initial one is about 5 minutes. Okay, so let's go over some best practices highlights. Now, it's pretty much everything that has to be for outdoor, for regular CSMA, CA still applies. So things such as proper RF line of sight needs to be observed, proper channelization, proper AP separation, proper frequency separations, things of that nature, and also things like pre-stage before deployment, especially particularly if the radios are out of reach, have extra equipment when deploying just in case some goes out, update the firmware of the devices before configuring. That's very important because the newer firmware actually changes the timing cycle. So the older firmware had a longer timing cycle. So if you have a TDMA device, I highly recommend you update the firmware. If not, then the initial timing could take up to like 30 minutes to an hour. So they actually reduced it to 10 minutes with a new firmware update. So I highly recommend you update in the particular way in which we recommend update. And then you engineer a solution using EnJet appropriately. You need to make sure whether or not EnJet is the proper fit or not, and whether or not that particular traffic type or the flow of traffic is appropriate for that EnJet that we currently have. And then also up there, you want to make sure you separate TDMA domains based upon traffic type and distance. And obviously, what we talked about earlier, do not set manual time slots in AP with EnJet enabled. And then do not set station priorities with large deltas between RSSI distance or traffic types. Same thing for CSMA CA, which we talked about. Okay, now it's time for some questions. So if you just type in the question and answer or the chat, which we'll be able to answer it. Okay, we have a question about what are the beamless of these. So as we stated before, TDMA does not change the actual physical aspects of the radio. It just changes the type of communication method, the timing. So the beamless are the same, the output powers are the same, the thresholds for ED are the same. All those are the same with a Wi-Fi chipset or a TDMA one. But thank you for that question. It's a very, 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 very good question. Okay, we have another question. All right, the other question is, we kind of alluded to it, but the question is, hey, they've noticed a higher latency over TDMA over regular CSMA CA. And we talked about that earlier. Basically, what happens is when you have a carousel going around, it introduces it's overhead, introduces a timing delay. And so, yes, your latency will be higher, but in our testing scenarios, what we've seen is that it's a steady one, not a variable one. So just as we have latency and jitter, we've noticed that jitter become less of a problem in TDMA than in CSMA CA because they actually have a predetermined time slot, or they could schedule their time slots appropriately. Okay, we have another question of what's the upper limit of EnJet and Station 5 ACs connecting to ENS 500 ACs? So I'm assuming he's talking about the number of participants. I would say on probably a light use would be 10, moderate use would be around 20 CPEs. And if you really want to push it, if they're really close and they have, they're far enough away from each other, they all have good line of sight, we're probably pushing around 50 to 100 CPEs. In that regard. Now remember, with TDMA, there's time slots. So as they start adding more participants, these set time slots had to be shared among other people. And so what happens is you get to the point in which you could add more to there, but they won't be able to push traffic because they're sitting there waiting for their time slot. And then effectively you have a network that's not working. So it's important based upon the traffic type to determine the number of CPEs that are participating in that, and you plan appropriately for that. We have another person that says, sounds like a fit for a wireless outdoor security camera solution, correct, with no other traffic? Yes, thank you, that's a good question. Basically, in that particular one, you do have a set traffic type, And all you need to do is just determine what the not what the average is, but what the median is. So you have low ends, you have high ends, because you obviously know what camera traffic with depends upon the lighting outside, depends upon the movement, depends upon a lot of these other factors, determines how much it's actually going to be dumping onto the network and when it needs to dump, and whether it's edge recording or non-edge recording. So yes, when it comes to camera traffic, this is perfect for it because you're actually getting away from contention. So you could deploy in much larger environments, but also taking into consideration that it does have its limitations as well. You need to make sure that these limitations, you need to make sure that it operates in the limitations so you're not trying to push too much that shouldn't be pushing down through there. But thank you for that question. It's a very good question. We have another question. I don't think it's for TDMA, but I could answer it anyways. It's someone stating they have a large church, 30 to 40 foot ceiling height, to use indoor outdoor APs. Most of our indoor APs are not connectorized, very few are. So I would say in this case, use an access point that is connectorized. If you have no climate control in that area of the building, then I would, like, let's say it gets hot because the AC doesn't touch that area, then maybe I would go for an outdoor access point that's connectorized. So I could put some antennas out, external antennas, and be able to actually have the access point in the environment that will survive. Yeah, if seating is that many people, about 1,000 people, you need to make sure you take a take rate, how many people are actually taking it, and then obviously design for the appropriate number of access points and channelize it appropriately. Yeah, these design questions for that are great as well. But TDMA doesn't help with that. TDMA is mostly helping for outdoor bridging. All right, so we have another question but thank you for that question. It's a great question. Another question is, do you recommend Ethernet surge protectors or lightning suppressions? Yes, we do. I'll even take it a step further and say we also recommend power conditioning as well, like uninterruptible power supplies, as the battery is going to condition the power before it gets to these devices. Most of the time what we've seen is some of the power issues in certain deployments, like in RV parks and stuff, is going to be the problem. And it's not just our equipment; it's other vendors too. By the time they get around to us, they've tried multiple vendors already, and they already had that problem, and they weren't able to address it. So, yeah, that's one thing to be able to look into, is the quality of power as well. But thank you for that question. We have another question. Is basically, can hardware version 1 and hardware version 2 connect with EnJet enabled? So that's a very easy one. The answer to that is no. They can connect, but not with EnJet. And does EnJet need to be disabled? Yes. So we do have a setup guide on our website that has a setup guide for hardware version 1 and hardware version 2 to set up in WDS bridge mode. The setup guide for hardware version 2 to hardware version 2 actually changes the mode. I know a lot of people are used to deploying it in WDS bridge, but we actually now recommend WDS AP to WDS station. That's the recommended mode now with EnJet. So I know it's kind of a change, kind of hard to get that out there to change people's mindsets. But yeah, with hardware version 2, we recommend WDS AP to WDS station. And with hardware version 1, we recommend WDS bridge still. But thank you for that. It's a very, very, very good question. Okay, we have another question here. What's the maximum distance that TDMA can be used? Well, that's kind of a loaded one right there, don't you think? So that's really a good question. It's really just like we were doing it for distances for your wireless bridge. As you know, there's a natural reduction to the signal to noise ratio as you start getting further away. There's a propagation delay as you start getting further away too, so that's got to be accounted for into the TDMA. That's why if you have asymmetric TDMA, you'll be able to adjust that for you. Just take a little bit longer to make the initial adjustment, and for participants going into there. So we recommend, if you're going to be, the same thing, distance for TDMA is the same for CSMA, CA. So you have to worry about your system operating margins, your Fresnel zone, the type of traffic, whether or not you have a good enough signal strength to modulate at the data rate that you want with a margin in there. So all that remains the same. It's just that you're using a TDMA. So if any case, like I stated before, you want to make sure that those clients that are further away are part of a separate domain than ones that are closer. That will give you the best performance for the TDMA. And as well, if you're using non-TDMA too, that will give you the best results as well. But thank you for that question. That's a very, very, very good question. Okay, so That's a kind of a good question too. All right, so someone's asking a question here of well, just a generic one. I'll answer it. They're looking for access to the slide deck. If you need access to the slide deck, we could always email it to you. Just email partners@ingenioustech.com, and we could get that slide deck out to you as well, so you could have a slide deck. We also have a recording of this that's going to be further released. If you check our Ingenious YouTube channel, it should be there as well. But thank you for that question. All right, we have a lot of great questions here, but we're running a little bit low on time. So anything I can't get to, I'll answer it later on. And so we got to get going. And thank you for your time, and hopefully to see you in the next webinar.